Close visual observation of a supercell can provide clues that tornadogenesis is about to occur, but there are a few radar signatures that can tip you off as well. The first of these is called a differential reflectivity arc, or ZDR arc for short, which is an area of increased differential reflectivity that usually occurs on the right edge, which is typically the southern edge, of a supercell's forward flank downdraft along the reflectivity gradient. The ZDR arc occurs due to a preponderance of oblate, or flattened raindrops that become confined to this region, a process called size sorting. The mechanism behind this size sorting process is the veering and strengthening of the winds with height, i.e. vertical wind shear, that occurs in supercell environments, as smaller raindrops that fall with lesser velocity are advected farther from their source region than larger raindrops that fall more quickly. On the same token, the ZDR arc is tied to storm relative helicity, which is essentially a measure of the potential for cyclonic updraft rotation in supercells, generally below 3 kilometers above ground level. Storm relative helicity is an estimate of streamwise vorticity in the environment. Vertical wind shear creates horizontal, rotating tubes of air, which is a manifestation of horizontal vorticity or spin. When the wind feeding into a storm blows parallel to these tubes, the wind itself is spinning and the vorticity is considered streamwise. When the wind blows perpendicular to these tubes, the wind itself is not spinning and the vorticity is considered crosswise. Streamwise vorticity ingested by a storm induces updraft rotation from the get-go, whereas many storm-scale processes must occur before an updraft in a crosswise vorticity environment can attain rotation. Think of it as a quarterback throwing a football to a wide receiver. If the quarterback throws the ball with a perfect spiral, the wide receiver can easily catch the ball and run it into the end zone for a touchdown. This is akin to streamwise vorticity. In contrast, if the quarterback throws a wobbly ball, the wide receiver may have to bobble the ball a bit before bringing it in, making the catch more complicated. This is akin to crosswise vorticity.
The Chaser Academy is our premium subscription, and it's the best deal in storm chasing. Link in the description.
Streamwise vorticity is much more favorable for inducing supercell tornadogenesis than crosswise vorticity. Therefore, because the ZDR arc is tied to environmental storm relative helicity and streamwise vorticity, a ZDR arc can be a sign that tornadogenesis may soon occur. The development of a ZDR arc can signal that a storm is experiencing increasing storm relative helicity and potentially greater streamwise vorticity ingestion, both precursors to tornado production. In addition, the separation between the ZDR arc and a feature called a KDP foot can indicate that tornadogenesis is imminent. A KDP foot is an area of enhanced specific differential phase that represents the heaviest precipitation within the supercell's core. Like the ZDR arc, the KDP foot arises from size sorting induced by vertical wind shear. Leffler and Kumjian 2018 came up with a separation vector drawn from the centroid of the KDP foot to the centroid of the ZDR arc. They determined that the separation vector's magnitude, i.e. the distance between the centroid of the ZDR arc and the centroid of the KDP foot, tends to maximize around the time of tornadogenesis. They also found that the separation vector tends to become more perpendicular to storm motion leading up to tornadogenesis, and that both storm relative helicity and streamwise vorticity tend to increase with increasing perpendicularity between the separation vector and storm motion. When the separation vector and the storm motion vector are more parallel to each other, the vorticity is more crosswise. In this example, reflectivity is on the top left, storm relative velocity is on the top right, differential reflectivity is on the bottom left, and specific differential phase is on the bottom right. The ZDR arc and its centroid, along with the KDP foot and its centroid, are denoted as in the previous graphic. The separation vector, abbreviated SV, and storm motion vector, abbreviated SM, are displayed off to the side of the supercell in the reflectivity panel with red and blue arrows respectively. The time relative to tornadogenesis is given in the top right corner. Notice how the separation vector and storm motion vector become more perpendicular with time leading up to tornadogenesis. In fact, in the scan just 3 minutes before tornadogenesis, the two vectors are nearly perfectly perpendicular to each other, indicating a shift to almost purely streamwise vorticity ingested by the supercell, and the tornado begins shortly thereafter. Mini supercells, especially those in more tropical environments, including those near tropical cyclones or their remnants, tend to display a mesocyclonic velocity enhancement signature, or VES, which is a small region of enhanced velocities greater than about 35 miles per hour between 7 and 14,000 feet above ground level on the right flank of a mesocyclone. VESs occur when many supercells deviate from the mean flow, which yields an asymmetric velocity pattern within the mesocyclone, and they tend to be located above the low-level inflow region and co-located with the low-level mesocyclone and hook echo. Velocity values within the VES tend to maximize 1 to 4 volume scans prior to tornadogenesis. Just like tornadogenesis, certain radar signatures can provide clues that tornado dissipation is about to take place. Many of you may be familiar with the occlusion process of a cyclic tornadic supercell. This occurs as the rear flank downdraft wraps completely around the low-level mesocyclone, cutting it off from the warm, moist inflow needed to sustain tornado production. As this occurs, you'll often see the TVS begin to turn to the left of its previous track on radar, sometimes even making a full loop before dissipating. A new low-level mesocyclone often develops close to where the old one was, leading to renewed tornadogenesis. Always be aware of the potential for leftward deviation near the end of a tornado's life cycle, as this can happen without warning and can lead to a perilous situation if you're located north of a tornado. In addition, several polarimetric signatures can develop in the lead-up to tornado dissipation. As described in Siegel et al. 2022, a decrease in intensity or disruption of the ZDR arc can be a sign that negative buoyancy is impacting the near-surface environment beneath the mesocyclone, which is unfavorable for tornado maintenance. This can also be a harbinger of decreasing near-supercell storm relative helicity. A decreasing angle between storm motion and the separation vector we just discussed can also indicate that tornado dissipation is imminent. Finally, precipitation within the hook echo tends to increase in intensity before tornado dissipation, which is often illustrated by an increase in KDP.
Remember to check out those links in the description below, and then watch another video.